In this video, we're going to talk about factoring out the greatest common factor, the first chapter in the first section of the chapter 10 on factoring in ORCA. So, factoring as an idea is going to be one of the main things we cover in this class, and the way to think about it to begin is to think of it as the distributive property, which is something that may be familiar to you from past math classes, in reverse. So let me begin from there. In a past math class, you may have had an expression like this. I'll just make something up. 3 parentheses x minus 1, close parentheses. And the idea, I think, of an expression like this, if I was to ask you to simplify it, would be because there's a number up against the boundary of a parenthesis here, and then there's 2 terms inside that parenthesis, that 3 is in what's called distributive position. So it would be something like this. Distribute the 3 to each of the 2 terms inside. 3 multiplied by x is 3x, and 3 multiplied by negative 1 is negative 3. So that would be simplifying or distributing. And factoring essentially reverses this process. It says, look at what are factoring the greatest common factor versus this process. I should be clear that this is one of many factoring techniques we'll learn. It's just the first one. So if you look at our expression 3x minus 3 and pretend for a moment that you didn't know where this had come from, you might look at it and think, well, what do these 2 terms have in common? Well, one thing they don't have in common is they don't both have an x. There's only an x in the first term, but not in the second. They do both have a 3. And this idea of factoring has at its heart division, in the same way that since it came from a distributive situation, and distribution is multiplication, to do that in reverse is sort of to divide. If you see that both of these terms have a 3 in them, you would say to yourself, it seems that these two have a common factor of 3. So to test that, you would write it as, well, if you factor that 3 out, it's like undistribution. So we can, and we're just conjecturing at this point. So suppose that 3 is a common factor. Well, then by dividing it out, something has to be left over. And we can do these kinds of processes one piece at a time. Can 3 be divided from 3x? Sure. What do you get? What remains when you divide 3x by 3? You just get the x. And then what remains from negative 3 when you divide it by positive 3? Well, negative 3 divided by positive 3 is negative 1. So just thinking that sort of forward and backward, we can at least think that we have this, that by factoring a 3 out of both these 2 terms, we end up with the sort of undistributed, or what's called the factored form. Now, we know this is correct because we started from this premise and distributed, but what if you didn't know that? What if you weren't sure that your factor was good? A really good way to check your factor as you're learning, and I encourage this, is to, assuming you didn't start from the distributive perspective, is to distribute it after the fact, essentially to check your work. So if it is correct that 3x minus 3 is the same as 3 parenthesis x minus 1, where the 3 is factored out, that should be, revealed if we just allow the distribution to take place. The 3 multiplies by the x and becomes 3x, and the 3 multiplies by the negative 1 and becomes negative 3. Oh, and we are back to where we started, which confirms that our work was good. So that's fine so far. Now that just meant that 3 was a common factor of 3x minus 3. Where we want to go in this chapter ultimately is what's called the greatest common factor. So the only difference is, if you factored out a common factor of 3 in this example, though, you have to be sure that you've done as much as you can. So the 3, it has been factored out, and I'm happy with that. I'm not going to redistribute it. What I want to consider, though, is in this parenthesis, in what's left, the x minus 1, are there any other common factors? In other words, is there anything else that x and negative 1 share from a divisibility perspective? And in this case, I don't think there is, other than a kind of trivial, you could divide both of them by 1, but that wouldn't really be a meaningful division. So what's left here with this x minus 1 has no more common factors, so I think this example is already complete, and I would say 3, the first thing I reached for, was not only a common factor, it's what's called the greatest common factor. And what that means is the best you can do from a common factor perspective. Let me just give another example. So here's another example. Well, let me think about this. How about to do this is not going to be a very complicated example, but just to say, how about 6x minus 6? And this is one where maybe the greatest common factor, that's too similar of an example. Let me make it 6x. Let me make it 6x plus 12. There, slightly more interesting. So, if you look at these two and think, well, I'm playing the game of factoring. I want to see what common factoring. I want to figure out what these two have in common, if anything. Once again, they don't both have an x, so we can't factor an x out of both of them, but we can at least look at the numbers. So, for this one, if you're thinking that the common divisor is 6, you would be right, but what if I didn't see that right away? One thing I will say is that since 6 is an even number and 12 is an even number, that means that both of these terms can be divided by 2. So 2 is technically a common factor. So let me run with that. I am factoring or dividing out 2, and then in parentheses, remember this is undistributing or reversing the distributive property, asking, well, what does it leave when you sort of siphon out a division of 2 from both of these terms? And we do them in steps. 6x divided by 2 is 3x. And then the positive 12 divided by 2 is positive 6. And you may verify this if you wish. If you redistribute the 2 into the 3x and into the 6, it should come back to 6x plus 12. Just saying that so far your work is good. And so that's fine. 2 is a common factor. But in this case, maybe you're looking at this and thinking, that's probably not the best we can do because what's left in the parentheses, the 3x and the 6, have more in common from a division perspective, from a factor perspective. They're both divisible by 3. So let me just say, well, this is 2 times this. So I could say it's 2, I'm going to leave that 2. I don't want to lose that 2. We already worked for that. But 3x plus 6, both of those can be divided by 3. So I'm keeping the 2 separate. But let me just stack this here and say I'm factoring out a 3 now from 3x plus 6. Don't want my work to get messy. But 3x divided by 3 is 1x. And 6 divided by 3 is 2. And now I can say that's good. Looking at what's left here, once again sort of checking to see if there's more I can do, I think I have pushed it as far as I can because x plus 2, the terms are so minimal and don't share anything in common from a division perspective that there's nothing further there. So what do I do then with the 6 and the 2 and the 3? They both factored out in 2 stages, and they're being multiplied by each other by the way this game was played. So now I can just let them merge into 2 times 3 is 6, and the x plus 2 remains. So the fact that I factored out a 2, then saw there was more to do, factored out a 3, which meant ultimately it's like I could have just factored out a 6 from the beginning, says that the greatest common factor of this expression was not 2, but 6. And and that's the greatest common factor. 2 was a common factor, 3 also was, but had I aimed or taken some more time to look at this, I might have been able to go straight for that, biggest move in one move. And there's nothing wrong with doing it in steps, but when it all comes together and your process can't go any further, that's when you've found the greatest common factor, which in this case is 6. We could check our work by distributing 6 times x, and 6 times 2 would definitely give us this. So for the remainder of this video, I'm just going to go through some quick examples of this, and we'll go over some more in class. I want to introduce some more negatives here. What if I have this? Oops. Negative 5x minus 5. So this one is worth mentioning It doesn't seem any worse than the others because we can see that each term has a 5. So a natural move might be to factor out 5. And if you factor out, and here's where I want to be specific, I'm factoring out a positive 5 intentionally. Well, what happens if I do that? I ask, negative 5x divided by positive 5 leaves what? Well, negative 5 divided by positive 5, 5's cancel, but the negative divided by positive doesn't cancel the negative, so it stays negative x, right? And sort of similarly here, if this is seeming gross, that's motivating our next thing. What happens when you divide negative 5 by positive 5? It's the same idea. It's not positive 1, it's negative 1. So this is a valid factor, I think. And if we FOILed it or distributed it to check, it would come back to the original. And, negative x minus 1 here in the remainder parenthesis, they're not too similar. I don't really like all those negatives, but I could say, okay, probably done. But I want to now pause and sort of reset this problem, because something I will mention again and again in this class is that sometimes you have more than one choice about what to factor, or what the best greatest common factor might be, or what it even is. So let me show you. Let me show you what I'm saying. To start again, here's the original. We factored previously a positive 5. I will argue that we can also choose to factor out from both terms a negative 5. So what would that look like? If we do that, we have to sort of start over. Negative 5x divided by negative 5. Well, this time, negative 5 divided by negative 5, since they are a dead match, that's positive 1, so they essentially cancel and just leave positive x. That's the difference of that negative. And a similar thing happens here. Negative 5 divided by negative 5, factored out, doesn't leave a negative 1, it leaves a positive 1. So let me just hold here. See how these look like mirror versions of each other. And I would say they both check out by distribution. They both check back to the original, so they're both technically good. So which is the greatest common factor, 5 or negative 5? They both are the greatest common factor in that they're both common factors and we can't do more once we've done them. So which do you do? I encourage you, when you have a choice like this with a potential for a negative common factor, to choose the one which, when you factor it out, leaves your leading variable, whatever it be, in this case it's just an x, which removes the negative from that. Like in this case, this x was negative, and that's not bad. It doesn't make the math impossible. It just makes future math potentially a little bit more gross. And this will become clearer once we've learned more factoring techniques. But just for now, to say, given the choice between two, kind of equally reasonable common factors, I encourage you to choose the one that leaves a positive coefficient for your leading term. All right, let's do another example. How about this one? 90r squared minus 20. And the idea is just look at the two terms. This is a two-term expression, and look for any and all common factors. And this time, since we've warmed up a little bit, I'll go straight to the greatest common factor. One thing to comment again here is that there's r to the power of 2 here, but there's no r's at all, no variables at all in that, so there's no common factor at all of a variable there. We will see examples where the variables are part of the common factor in class. But within the numbers 90 and 20, there are several divisors in there that are in common. Both even numbers, so 2 is in there. I think 5 is a divisor of both of those numbers. But I think just stepping back and remembering divisibility, I think 10 is a divisor of both 90 and 20. So, and the bigger the number you can factor out of everything, the quicker you get to the payoff. So let's go for 10, positive 10. If I factor a 10 out, of 90r squared, I think, what's 90 divided by 10? That leaves 9, and the r squared is still there, of course. And then if I say, well, what's negative 20 divided by positive 10? That's negative 2, because a negative divided by positive is still a negative. So there it is, and if we want to check our work, we can redistribute and just look at it and think, yes, 10 times 9r squared is 90r squared, and 10 times negative 2 is negative 20. So it checks out, but the real question here is, are we done? Because this as a remainder looks much grosser than the previous ones, but consider it in the same way. Can we factor any variables at all out? No, because there's r squared in the first term and no r's at all in the second term. And this time, even though there are numbers, this is a 9 and this is a 2 or a negative 2. And if we think about what divides 9, you can divide 9 by itself or by 3, and that's basically it. And 2 can only be divided by itself. So it's something about the particular numbers faced off against each other. They, with respect to each other, have no common factors. So even though this is grosser than the previous examples, there's nothing more that can happen with this piece. So we are in fact done. 10 is the greatest common factor for this expression. And before I end the video, I'm going to do one more quick example to show you something that can happen, something that can go wrong. I'm going to say 5x squared plus 11. If possible, pull out the greatest common factor. So I've been going along this by first looking at all the terms and looking to see, do they have any variables in common? And none of them have so far, and this one also doesn't. There's an x squared in the first, and no x's at all in the second. So no variables in common. So then I give up on that and move on to the numbers. 5 and an 11. Now, it depends on how comfortable you are, how long it's been since you've thought about divisibility, but you may recall that there's something called prime numbers. And we can talk about this, but prime numbers are numbers that have no divisors other than 1 and themselves. And 5 and 11 are both prime numbers, which for the purpose of this just means that they don't share anything at all in terms of divisibility. They are, other than 1, and I should comment, I could always write this is the same as 1 times 5x squared plus 11. But if you look at a divisor of 1, you immediately see that it's not worth much, because you divide something by 1, it doesn't change at all. So I'm not going to do that. But aside from that sort of trivial factor, can't get any x's at all, and 5 and 11 don't play nicely together, so it seems like this one has no meaningful greatest common factor, which means it cannot be factored. And that doesn't mean we have broken anything, it just means there will exist the occasional expression which is called, and I don't want to say equals, because it is prime. And if something is prime, an expression can be prime sort of in the same way that a number can be prime, meaning it is not meaningfully factorable. There's nothing you can do to it. It's sort of finished on arrival. And this is an example of a prime expression. There's no common factor of worth and nothing can be done. So we just acknowledge that and leave it alone.